This is a refutation of algebra and a more formal and concise presentation of the same argument I presented in the previous and more lengthy discourse. I primarily mean here to contend against the idea that quantities of different orders of magnitude may be equated with the product of quantities of different orders of magnitude, having different units of measure, different kinds of units of measure. Such as that the area of a surface may be equated with the product of quantities of length, and that quantities of length may be equated with the quotient of quantities of surfaces or areas, which are different units of measure. There are three arguments I composed in the form of a reductio ad absurdum. By which I mean to argue against that position. I will start with the most general. Suppose there to be a given surface, such as that of a square or a rectangle. Now, a surface may obviously be divided in half, and the area of a surface may likewise obviously be divided in half. Let it then be so divided. It will be divided then into magnitudes of half the area of the given surface. That is to say, it will be divided into smaller surfaces and not into quantities of length. Now, those two magnitudes of lesser area into which the surface was divided may also be divided in half. Let them be so divided. They will be divided again into magnitudes of lesser areas than they. They will be divided into surfaces or areas, but not into quantities of length. But since not only are lines infinitely divisible into smaller and smaller lines, but surfaces likewise are divisible ad infinitum into smaller and smaller surfaces, but never into lines. The magnitude of the surface divided and thus diminished will never be exceeded or equal to, will never be exceeded by or equal to the quantity of length of its side or its base. Now, Euclid defines the ratio between magnitudes thus. He says, magnitudes have a ratio to one another which are capable when multiplied of exceeding one another, which are capable when multiplied of exceeding one another. If then a surface may be divided into lesser and lesser surfaces, and so on ad infinitum, and will never, when thus diminished, be exceeded by the magnitude of a length. How can a surface will not then be divisible into quantities of length? For the magnitude of a surface can never thereby be exceeded by any quantity of length. How can a surface, or the area of a surface, be rightly conceived of as the product of quantities of length, or as being divided into quantities of length? If a surface may be divided into lesser and lesser surfaces, but never into lines, and the magnitude of a surface, when thus divided, will never be exceeded by the magnitude of a line. How can a surface be a multiple of quantities of length, or divided into quantities of length? That is the first argument. And these problems arise from the infinite divisibility of continua, but from the infinite divisibility of each of different orders of magnitude, as surfaces are infinitely divisible into surfaces of smaller and smaller magnitude, as lines are infinitely divisible into smaller and smaller lines, but never into points. A surface cannot then be divided into quantities of length. The second argument takes rather the inverse approach as to what sense there might be in squaring the numerical value of a measured line. Or in what sense there might be, generally speaking, in considering the area of a surface as the product of the numerical value of a line. This at once is the inverse of the previous argument and contains two reductio ad absurdums regarding what sense there might be in squaring the numerical value of a line. For that must be either the calculation of the numerical value of a surface or of the line multiplied only in length. If, however, the area of a surface is meant to be calculated by squaring the numerical value of a line. The area of the surface, or the square, must have a numerical value of the same units of measure as the linear magnitude that is to be squared. For the multiple of a number of any units of measure can only be a greater number of the same units of measure, not of different units of measure. A multiple can only be a greater number of the same units of measure. But the square of a line with the numerical value of 2 suppose there then to be a line with the numerical value of 2. And let it be squared. And suppose also that by what is meant by the square of its numerical value is the quantity of a surface, of a square. That square will then have the quantity of 4. But such a square, having the side with the numerical value of 2 and 4 sides, will have a perimeter of 8 units of length. If then the numerical value of 4 attributed to the area of the square is of the same units of measure as the side of the square, the magnitude of the area will be less than the magnitude of the perimeter, which is absurd. For the area having the numerical value of 4, if those are 4 of the same units of measure, will be less than the magnitude of its perimeter, which has the numerical value of 8. But the magnitude of an area cannot be less than the magnitude of its perimeter. Such an area with the numerical value of 4 must then have different units of measure than those of the length of its side. The area of the square must be of different units of measure than its side. But the multiple of a number of any units of measure, the multiple of any quantity, cannot be a number of different units of measure, but can only be a greater number of the same units of measure. So, what is meant by squaring the numerical value of the length of a line cannot be the numerical value of an area or of a surface, as surfaces have different units of measure than lengths of lines, as must be the case if the surface of a square cannot have a lesser numerical value than that of the length of its sides. The magnitude of a square cannot be less than the magnitude of its perimeter. They must then be of different units of measure. But if there are different units of measure, how can the square be a multiple of the quantity of length? For a multiple can only be a greater number of the same units of measure. But then what is meant by squaring the numerical value of a line can only be the length of a greater line, rather than the numerical value of a surface. However, in that case, the square of the whole line segment ought to be equal to the square of all its parts. I mean that whatever may be the number of measures of the line to be squared, the square of the greater number of smaller measures should be equal to the square of the lesser number of greater measures of the same line. But we find that not to be the case. For squaring the number of meters and squaring the number of centimeters of a line of the same length produces different lengths and does not result in the same length. I mean that a line with 2 parts and a line with 4 lesser parts, when squared, results in different lengths. When that product is not conceived of as an area, but a line. And this is the case with geometrical lines, but I am presenting the more tangible case between physical units of measure. For the argument is the same regarding both. The number of seconds and the number of minutes of the same span of time are, when squared, different amounts of time. And a line with the length of 2 yards, for example, which is the same as 6 feet, is, when squared, different lengths, when those lengths are conceived of as a greater number of units of length and not as areas. 2 yards is the same as 6 feet. That is the same distance. Yet if we square 2 yards and we square 6 feet, we get different lengths. The square of 2 yards is 4 yards, which is also 12 feet. While the square of 6 feet is 36 feet, which is the same as 9 yards. Thus, the square of the same length is different lengths and not the same. The square of 2 yards and the square of 6 feet, though they are the same length, are different lengths. The square of 2 yards is 4 yards or 12 feet. And the square of 6 feet is not 4 yards or 12 feet, but 36 feet or 9 yards. Thus the same length when squared is both 4 yards and 9 yards, or 12 feet and 36 feet, which is absurd. But if the square of the number of measures of a line is not equal to the square of half measures, of the number of half measures of the same line, then neither can squaring the numerical value of a line mean multiplying its length. That is, even geometrically, even when we don't assign them physical magnitudes. Though I had in mind here Galileo's law of acceleration, of the square of the distance fallen. The square of the time of a distance fallen. The square of a distance fallen. But even geometrically, the same line, when thought of as composed of 2 parts, or of 2 units of length, and when thought of as 4 units of lesser length, is when squared different lengths. For a line with the numerical value of 2 units of length, or consider this. The same line, when considered of 2 greater units of length, when squared as the square of a length of 2, will result in the length of 4 of those units. And the same length, when thought of as having 4 lesser units of length, will be when squared 4 of the total, will be 4 of the total distances or lengths. And when divided into 16 lesser parts, as the square of the length of the numerical value of 16 units of length. We'll call for that same portion, the same whole length, to be multiplied instead of twofold and instead of, in the second case, fourfold, 16-fold. And since a length is infinitely divisible, since a line is infinitely divisible, squaring the greater number of lesser parts will produce a greater total distance than squaring the lesser number of greater parts. But that is absurd.